Let's give one more example of admissible filter find module dimension 1. So last time we have discussed, the last part of the exercise, I've discussed for a one-dimensional filter find module, when is it admissible? Let's quickly recall what we have done last time. Recall that, so if we have filtered find module over K with dimension 1 as a K0 vector space, for it is bijective, then we recall that we have choose basis D, suppose this phi of D is, because it's bijective over D, means map over D, so this is the one-dimensional cases again for some lambda K0 star, because this is bijective, cannot be 0. N is nilpotent, implies that this ND as a subspace of D, either 0 or D itself, must be 0. If ND equals D, then this cannot be nilpotent. And so N is 0. What is left is the filtration. Because this is one-dimensional, one-dimensional over K, and so there exists some R such that filtration of dk, it has jump of filtration, right? This is the jump happens here for R, and so by our definition of Newton number and Hodge number, this Newton number is obviously p-adic evaluation of lambda, because I'm thinking of is what happened if I'm changing D. Changing D should just gives you, should not change the p-adic evaluation. That's why it's well defined, right? Just quick recall, how do we define the Newton number for dimension 1 find module? The definition is just choose some basis for it. You should fix some basis for this one-dimensional, and then whatever the basis it is, you use frobenius to apply on it, and you just pick out this coefficient. And we have proved that this doesn't, the p-adic evaluation doesn't depend on the choice of the basis. Yes, this is it. And then the Hodge number is the jump of the filtration, so this is R here. Therefore, D is admissible if and only if p-adic evaluation of lambda equals 1. So notice that if you twist, we have proved that this is admissible if and only if this is. Right, so imagine if you do that twist, then obviously this twist will change this hash number of it, right? Because it's shifting the filtration. By that matter, it will also change this correspondingly. The hash number will be changed correspondingly, because the Frobenius would acting on this new basis after that twist, and they will produce some p power which will change the p-adic evaluation, but finally it will be the same. Okay, so let's continue with today's exercise. What we're going to do is we want to look conversely. So let's create some admissible ones. Start with any lambda in K0 star. We can associate to it what is called d lambda. We're going to define this. We're going to define admissible filter defined module as follows of dimension 1. So we have to describe as a module. This is just K0 looks one-dimensional, and Frobenius rate is lambda composed with sigma tensor 1, or lambda times sigma tensor 1. Monodrom is 0. As we discussed, it must be 0 if it's admissible, and we have discussed if it's admissible, then the p-adic evaluation of lambda must be some r, and r corresponding to the filtration. And so here the p-adic evaluation of this Frobenius obviously it will be p-adic evaluation of lambda. So the filtration, the jump must happen if it's admissible at, and that's the only requirement by our criterion. The jumping index must happen exactly at Vp lambda. So if we define the filtration this way, it will become admissible. Okay, this finish our construction of admissible filter defined module. The exercise is proof. We're going to classify them. Prove that for any two different lambda prime in K0 star, then this d lambda, as we just described or constructed, is isomorphic to d lambda prime. Of course, this is isomorphism in here as a filtered defined module. If and only if the condition and it happens on the lambda and lambda prime, the relation between them, if and only if there exists some unit element in WQ star such that lambda prime equals lambda times sigma u over u. So let's prove this. So remark is that, okay, one thing must be sure that if you have isomorphic filter defined module, then this jumping of index must be the same position, right? They must have the same hash number. We haven't done exercise of this, but we will do this maybe someday. So let me put a remark here. If you have bijective homomorphism in filtered Q-vector space, then this hash number of D1 would be less equal than the hash number of D2, and with equality if and only if F is an isomorphism in field of K. In other words, it is a street morphism. So this is a lemma, and you could think of this as a sub-exercise. We will discuss this someday. So I'm just put this remark here to tell you that this looks good for our intuition, because this is telling you that the Harsh number should be the same. But here, yeah, actually I'm telling you that this implies the Newton number are the same, because Newton number is just p-adic evaluation on this kind of eigenvalue lambda and the kind of eigenvalue lambda prime. If they're different by sigma u over u, then this, as we have discussed before, the p-adic evaluation is 0 for this sigma u over u, and so they have the same p-adic evaluation. So this will tell you that this is not yet the proof, but just before we prove, when we see this, we are good to see this. This already implies that Newton number of d lambda equals the Newton number of d lambda prime, right? Okay, let's do the proof. So firstly, let's say this d lambda is telling us that it is just Q0 vector space, and in particular you could, let's fix a basis on 8, and for d lambda prime, let's fix a basis of 8. And then this Frobenius over this d would be, just by the definition of d lambda, it would be just lambda and sigma tensor 1 over 8, and then this is just lambda of d. Similarly, this phi prime over d prime would be lambda prime of d prime. And so the question is, when is it isomorphism? So we want to claim that isomorphism if and only if this lambda prime and lambda different by sigma u over u. So let's suppose it's isomorphism. Suppose it's isomorphism. In other words, this implies that there exists some f Q0 linear, right? Q0 linear map f from d lambda to d lambda prime, and so it maps basis to basis, which means there exists some u in Q0 star. Making this, let me think, K0 star or yeah, K0 star, such that, so it have to be this is obviously isomorphism as just Q0 vector space, but it have to be compatible with the filtration and Frobenius. Let's first check the filtration, the Frobenius. So f phi of d have to be the same as Frobenius prime f of d, right? This left hand side is f of ud prime, which is then k linear, K0 linear, so f of, sorry, so this is lambda of d, this is K0 linear, so this is lambda of fd is ud prime. On the right hand side, we have phi prime of fd, so phi prime of fd is ud prime, and phi prime is, so both phi and phi prime semi-linear, so sigma of u, and then phi prime of d prime, which is d prime, lambda prime d prime. And so this implies that this is isomorphism, is telling because this is under basis and in one-dimensional vector space, lambda u equals sigma u times lambda prime. because u is unit, so sigma u would again be a unit, and this tells you that lambda equals sigma u over u prime. Okay. And the isomorphism, and the conversely, just if lambda equals this sigma u over u lambda star with u in k0 star, then you could construct such a map from d lambda to d lambda prime, just map d to this u of d prime, and then this is this will be compatible with the Frobenius, right? And one just quickly check this filtration. It's also the same because we jump at the same index, which is the p-adic valuation of this element. Yes, this is finished the proof. Okay, so sub exercise is I'm looking at this condition here, is saying that u is in wk star, but what I'm writing in my proof is that u is in k0 star. What is the difference? K0 is wk, invert p, and then takes a star. And so for example, this means that if my u is taken to be one over p, then it's here, but it's not there. Let's see what happens if this is the case. If I'm mapping u to 1 over p, then sigma u over u would just be identity, right? It doesn't matter. Is this stopping me from being isomorphism filtered modules? So mapping this space element to 1 over p of d prime. Is this a problem? Is this a problem? No, this is not a problem. This is okay. It doesn't matter because you could fix whatever. This is not hurting the this is not hurting p evaluation, because even if I mean, anyway, yeah, this is again compatible with this Frobenius structure, because as we proved, what the difference is just phi over u, and sigma u over u, and whatever from 1 over p, this is still true. Sigma u over u is just 1. Yeah, no problem, I think. So let me modify it to the statement, not necessarily here, just in case 0 star.